Your grandfather's Johnson fires up after decades while your neighbor's new 4-stroke needs its 3rd warranty repair. These weren't just motors, they were engineered investments that manufacturers stopped building when they discovered planned obsolescence generated more profit. However, the real question isn't why they lasted so long, but why the marine industry deliberately stopped making them. Built to last means surviving saltwater, amateur mechanics, and owners who thought winterization was optional. That's exactly what we're measuring as we examine the engineering that made these power plants legendary, starting with OMC's most audacious creation. The Evinrude 300 XP wasn't just an outboard, it was over-engineered to the point of being offensive. This late 1980s monster packed a cross-flow V8 displacing 4 liters, producing power numbers that made competitors question their life choices. The loop-charged combustion chambers delivered surprising fuel economy for a power plant this size. What made the 300 XP special was cast iron cylinder liners pressed into aluminium block. Those liners could be bored multiple times, meaning worn engines needed machine work, not replacement. The powerhead used gear-driven design, eliminating belts or chains. OMC equipped these motors with oil injection that actually worked. The electrical system was marine-grade from factory, with sealed connections staying sealed. The lower unit featured massive gears handling the torque. These engines survived because they were designed with realistic service intervals and durable parts. Maintenance was straightforward. Change lower unit oil twice per season, keep oil reservoir filled with quality 2-stroke oil, replace water pump impeller annually. These weren't maintenance-free, but they were maintenance-friendly. But wait until you hear about the Johnson that started this revolution back in 1978. The 1978 Johnson 235 represented when OMC decided recreational boaters deserved real power. This V6 displaced 2.6 liters and introduced features defining performance outboards for 2 decades. The loop-charged design with reed valve induction improved fuel atomization and reduced unburned fuel plaguing earlier 2-strokes. Johnson equipped this motor with solid-state ignition, eliminating points and condensers. The block casting was thick enough for multiple rebuilds. OMC used cross-flow head design, keeping intake and exhaust ports separated, reducing thermal stress. The crankshaft rode on roller bearings rather than plain bearings, dramatically extending service life. These engines survived decades because they operated within comfortable margins. The cooling system kept temperatures stable during prolonged runs. The mechanical fuel pump was driven off the crankshaft. One less electrical component to fail. The torpedo-style lower unit had adequate gear ratios for heavy boats. Maintenance was modest by modern standards. Mix fuel at 50:1, change lower unit lubricant seasonally, replace water pump impeller every other year. Johnson designed this motor before planned obsolescence. The next engine proved loop-charged technology could deliver even more reliability. The Evinrude 200 XP earned its Looper nickname from revolutionary loop-charged combustion chambers, transforming 2-stroke efficiency. Introduced mid-1980s, this V6 displaced 3 liters, delivering smooth, reliable power favored by fishermen and tournament skiers. The loop-charged design directed intake and exhaust flow circularly, dramatically improving fuel atomization and reducing raw fuel dumped overboard. Evinrude built the 200 XP with split crankcase using through bolts rather than studs, creating a powerhead disassembled without specialized tools. Cylinder walls featured chrome plating directly applied to aluminium bore, eliminating separate liners while providing wear resistance lasting hundreds of hours. The VRO oil injection pumped oil proportionally to throttle position, ensuring proper lubrication across RPM range. These motors survived tolerating less than perfect conditions. The cooling system incorporated pressure relief, preventing block damage if debris blocked intakes. The electrical system used marine-grade components with proper corrosion protection. Reed valves were accessible without removing powerhead. Service requirements stayed reasonable. The VRO system required quality 2-stroke oil. Lower unit maintenance followed standard schedules. Water pump impeller lasted 2 seasons with proper flushing. The 150 class engines offered something more practical for average boaters. The Johnson 150 GT represented the sweet spot. Enough power without fuel consumption and complexity of larger motors. This high-output V6 used the same basic architecture as bigger siblings, but with a displacement dialed back to approximately 2.6 liters. Johnson achieved power through aggressive porting and timing, maximizing performance without sacrificing reliability. Block construction utilized aluminium with pressed-in steel cylinder liners, providing best characteristics of both materials. Johnson specified roller bearings throughout the crankshaft, and connecting rods featured needle bearings at the small end, reducing friction and extending life. The capacitive discharge ignition fired plugs reliably even with weak battery voltage. Failure resistance came from conservative engineering and quality components. The fuel pump delivered adequate volume with pressure margins accommodating partially clogged filters. The water pump housing used bronze rather than cheaper alloys, resisting corrosion. The exhaust system incorporated tuned chamber, enhancing torque while protecting internal components. Maintenance stayed straightforward. Oil injection required periodic inspection, but failures were uncommon. Lower unit service involved easily accessible drain plugs. Replace water pump impeller, change lower unit oil, keep oil reservoir full. The next engine pioneered features revolutionizing tournament bass fishing. The Johnson 175 Fast Strike arrived when tournament bass fishing demanded instant hole shots. This early 1990s V6 displaced approximately 2.6 liters, but featured radical port timing and tuned exhaust, delivering power characteristics closer to larger displacement motors. Johnson named it Fast Strike because it reached plane faster than competitors, critical when every second counted. The powerhead used OMC's mature V6 architecture, with upgrades targeting reliability under sustained high RPM. The crankshaft featured additional counterweights reducing vibration, and main bearings used larger rollers distributing loads effectively. Johnson specified upgraded reed valves with stiffer petals, maintaining sealing integrity at elevated RPM. The cylinder head incorporated additional cooling passages around exhaust ports, preventing thermal damage. These motors survived because Johnson built them during peak two-stroke refinement, before emissions forced compromises. The ignition featured individual coils per cylinder, eliminating cascade failures. The fuel system used pulse-driven pumps, with adequate flow without electric pump complexity. Maintenance allied with serious use. Oil injection required quality synthetic two-stroke oil handling sustained high RPM. Lower unit service became more critical with performance use. The ultimate expression came in the 250 XP's massive displacement. The Evinrude 250 XP represented OMC's two-stroke V6 apex with massive 3.6-liter displacement. This wasn't simply a bored-out smaller motor, but purpose-designed power plant for boats needing serious thrust. Evinrude engineered the 250 XP with larger bore spacing than smaller V6 models, allowing thick cylinder walls surviving multiple rebuilds. Loop-charged combustion chambers featured aggressive porting, maximizing power while maintaining shocking fuel efficiency. Internal components reflected serious engineering rather than cost-cutting. The crankshaft weighed considerably more than smaller motors, utilizing mass to dampen harmonics, destroying lesser engines at sustained high RPM. Evinrude specified main bearings with load ratings exceeding requirements. Connecting rods used forged construction with additional material around bearing journals. Survival characteristics stem from OMC's willingness to overbuild critical components. The electrical system used marine-grade connectors with genuine sealing. Fuel delivery incorporated multiple filters and high-capacity pump, maintaining pressure with marginal fuel quality. The cooling system kept temperatures stable during extended trolling or wide-open throttle. Maintenance reflected motor's displacement. VRO required premium synthetic two-stroke oil, non-negotiable for longevity. Lower unit service needed attention every 50 hours or seasonally. Johnson's response came with their own performance-oriented V6. The 1994 Johnson 200 Venom arrived during the final golden age of two-strokes, incorporating every lesson OMC learned. This V6 displaced approximately 3.3 liters, with loop-charge technology refined to near perfection. Johnson designed the Venom specifically for bass boats and performance applications, where acceleration and top-end speed mattered more than fuel economy. Powerhead construction used techniques perfected through generations. The cylinder block featured Siamese bores with chrome plating applied directly to aluminium, eliminating separate liners while providing excellent wear characteristics. Johnson specified larger main bearings than necessary, providing margins tolerating momentary lubrication failures. The crankshaft ran true after hundreds of hours because OMC used quality steel. These motors earned legendary status because Johnson got fundamentals right when competitors cut corners. The cooling system incorporated redundant pathways, ensuring water reached critical areas even with partial blockage. Ignition used individual coils mounted in protected locations. The fuel pump maintained consistent pressure across RPM. Service remained reasonable despite performance orientation. Oil injection needed quality two-stroke oil, but consumption stayed modest. Lower unit maintenance followed standard schedules. Johnson designed wear items actually replaceable by owners with basic skills. For ultimate power, Johnson built something more impressive in their V8. The Johnson 300 GT represented OMC's ultimate statement in recreational marine power. This V8 flagship displaced nearly 5 liters, delivering power that left competitors gasping. Johnson designed the 300 GT when regulatory pressure hadn't forced compromises, allowing engineers to optimize for performance and reliability. The motor featured cross-flow design with loop-charged cylinders in 90-degree V configuration, providing smooth delivery and balanced operation. Construction quality bordered on industrial equipment rather than recreational engines. Block casting used thick walls with adequate material for multiple boring operations. OMC specified main bearings with massive load capacity, and crankshaft rode on roller bearings sized for motors producing significantly more power. Connecting rods featured forged construction. Survival reflected engineering priorities lost in modern motors. Ignition featured 8 individual coils with separate high-tension leads, eliminating cascade failures. Fuel delivery used dual pumps feeding common manifold, ensuring adequate supply if one underperformed. Maintenance scaled with motor's size. Oil injection demanded premium synthetic two-stroke oil, consumption increasing proportionally with displacement. Lower unit service became critical because torque stressed gears. Water pump impeller replacement followed annual schedule. Sometimes the most impressive reliability came in smaller packages. The 1990 Yamaha 25HP proved Japanese manufacturers understood marine reliability differently. This two-stroke featured two-cylinder inline configuration displacing approximately 430 cc, with engineering refinement shocking mechanics accustomed to domestic motors. Yamaha designed the 25HP with overhead camshaft valve timing controlling intake track, unusual on small two-strokes, improving fuel efficiency and throttle response. Powerhead construction demonstrated Yamaha's commitment to longevity. Cylinder block used aluminium with steel liners press-fit and retained with mechanical locking. Crankshaft rode on ball bearings selected for load capacity exceeding normal requirements. Yamaha specified connecting rods with generous bearing surfaces and proper heat treatment maintaining dimensional stability. These Yamahas survived decades because engineering understood real-world marine conditions. Cooling incorporated oversized water passages resisting blockage from debris and corrosion. Fuel used pulse-driven pump with simple check valves. Ignition incorporated flywheel magneto generating sufficient voltage firing plugs regardless of battery condition. Maintenance bordered on negligible. Mixed fuel at specified ratio with quality two-stroke oil. Motors started reliably season after season. Lower unit changes required 5 minutes. Water pump impeller lasted multiple seasons flushed with fresh water. Another legendary small motor came from Johnson's classic Seahorse line. The 1985 Johnson 25 Seahorse represented final evolution of OMC's legendary small motor design tracing lineage back decades. This two-cylinder two-stroke displaced approximately 430 cc, featuring refinements accumulated through generations. Johnson designed the Seahorse with manual tilt and twist grip throttle control, eliminating complexity and failure points from power trim and remote controls. Construction reflected OMC's understanding of abuse in small outboards. Block casting used thick aluminium with integral cylinder liners. Crankshaft rode on ball bearings with adequate load ratings and proper sealing keeping lubricant in, water out. Johnson specified forged connecting rods with sufficient bearing surface. Survival stemmed from simplicity and robust components. Ignition used flywheel magneto with conventional points and condenser. Technology mechanics understood and could service anywhere. Carburetor featured simple float bowl design with accessible jets. Cooling incorporated adequate water passages resisting blockage. Maintenance reflected motor simplicity. Mixed fuel at 50:1 with quality two-stroke oil, though these tolerated variations better than modern engines. Lower unit changes required basic hand tools and 5 minutes. Water pump impeller needed replacement every other season. Even smaller motors demonstrated exceptional reliability when properly engineered. The 1980 Evinrude 15 HP represented minimalist marine power done correctly. This single-cylinder two-stroke displaced approximately 350 cc, featuring engineering so straightforward that failure became almost impossible. Evinrude designed the 15 for tiller steering with manual starting, eliminating every electrical component except ignition. Loop scavenged combustion with reed valve induction provided smooth power across RPM. Powerhead construction used techniques proven over decades. Cylinder consisted of aluminium with chrome-plated bore, providing excellent wear without separate liners. Evinrude specified connecting rod with adequate bearing surface and proper heat treatment preventing distortion. Powerhead bolted together with through bolts in simple pattern, making disassembly straightforward for first-time rebuilders. These tiny motors survived because Evinrude eliminated unnecessary complexity while retaining essential durability. Ignition used flywheel magneto with points and condenser, components rarely failing, requiring only periodic adjustment. Carburetor featured simple design with manual choke and accessible jets. fuel-incorporated gravity-fed tank with built-in filter. Lower unit used single forward gear without reverse. Maintenance approach negligible. Mixed fuel with two-stroke oil at proper ratio. Motors ran reliably for decades. Lower unit changes required minutes. Water pump impeller lasted multiple seasons. Mercury's contribution came with their legendary Black Max. The 1986 Mercury Black Max 200 HP achieved legendary status among performance boaters and tournament fishermen. This V6 two-stroke displaced 2.4 liters, featuring engineering prioritizing power and reliability over emission compliance. Mercury designed the Black Max with high compression combustion chambers and aggressive port timing, extracting maximum horsepower from modest displacement. The motor featured Mercury's proprietary electronic fuel injection, rare on two-strokes in 1986. Powerhead construction reflected Mercury's racing heritage. Block casting used thick walls with adequate material for boring during rebuilds. Mercury specified main bearings with load capacities exceeding requirements, providing insurance against momentary oil starvation. Connecting rods used forged construction. The Black Max survived decades because Mercury understood performance requirements. Ignition used individual coils per cylinder with electronic triggering, eliminating points and condensers. Fuel injection featured dedicated oil injection pump metering lubricant proportionally. Cooling incorporated pressure sensors and temperature monitoring, providing early warning. Maintenance reflected performance orientation. Fuel injection demanded quality two-stroke oil meeting Mercury specifications. Lower unit service became critical because performance stressed gears. Water pump impeller required annual replacement. Sometimes controversial designs proved more durable than critics expected. The 1995 Evinrude 70 HP VRO generated endless debate, with critics condemning the variable ratio oiling while defenders pointed to decades of reliable service. This three-cylinder two-stroke displaced approximately 1.15 liters, featuring Evinrude's controversial oil injection eliminating premixing. The VRO pumped oil proportionally to engine RPM and load, theoretically providing optimal lubrication while reducing consumption. Powerhead construction used proven OMC architecture refined through years. Cylinder block featured aluminium with chrome-plated bores, providing excellent wear resistance. Evinrude specified crankshaft riding on ball bearings with adequate load capacity. Connecting rods featured forged construction. Powerhead assembly incorporated loop-scavenged combustion chambers with reed valve induction. These motors survived because VRO actually worked when maintained properly, despite persistent myths. Oil injection pump featured simple construction with easily inspected check valves. Fuel delivery used pulse-driven pumps providing consistent pressure. Cooling incorporated adequate water passages. Maintenance centered on controversial VRO. Keep oil reservoir filled with quality two-stroke oil meeting Evinrude specifications, non-negotiable for longevity. Replace fuel filter regularly. VRO required periodic inspection of lines and pump operation. Four-stroke technology eventually proved its own durability credentials. The 2001 Honda 8 HP four-stroke demonstrated modern engineering could deliver exceptional reliability in small packages. This single-cylinder motor displaced approximately 130 cc. Featuring overhead valve design with timing chain rather than belt drive, eliminating common failure point. Honda brought automotive-grade components scaled for marine use, with horizontal cylinder orientation minimizing powerhead height while maintaining proper oil circulation. Construction reflected Honda's manufacturing discipline. Cylinder block used aluminium with cast iron sleeve, combining lightweight with excellent wear characteristics. Honda specified proper bearing dimensions and heat treatment, maintaining integrity through temperature cycling. Valve train incorporated hydraulic lash adjusters, eliminating periodic adjustment, critical for owners neglecting maintenance. These small Hondas survived because engineering understood simplicity and quality mattered more than features. Electronic ignition required no maintenance. Carburetor featured automatic choke working reliably. Cooling thermostat maintained optimal operating temperature. Honda specified seals keeping water out longer. Maintenance remained modest. Change engine oil every 100 hours using Honda-specified lubricant. Service lower units seasonally. Replace spark plug when performance degraded. Water pump impeller required replacement every other season. Honda designed the 8 HP for owners wanting simple, reliable power. Another manufacturer quietly built four-strokes, outlasting flashier competitors. The 2007 Tohatsu 9.8 HP four-stroke represented the most underrated motor in this discussion. This two-cylinder engine displaced 209 cc, featuring overhead valve design with timing chain drive, bringing industrial-grade reliability to small outboards. Tohatsu engineered the 9.8 with philosophy prioritizing longevity over marketing features, creating a motor surviving abuse, killing competitors. Construction exceeded expectations for motors in this price range. Cylinder block featured aluminium with cast iron liners providing exceptional wear resistance and ability accepting oversized pistons during rebuilds. Valve train used shim-adjusted valves rather than hydraulic adjusters, providing longer service intervals while maintaining precise timing. These Tohatsu survived because engineering understood marine conditions automotive engines never faced. Electronic ignition required no adjustment and resisted moisture excellently. Carburetor featured accelerator pump for crisp throttle response. Automatic choke worked reliably across temperature ranges. Tohatsu specified seals actually keeping water out. Maintenance followed predictable 4-stroke patterns with extended intervals. Change oil every 100 hours. Service lower unit annually. Replace spark plugs every 200 hours. Tohatsu designed the 9.8 HP before marketing demanded features compromising reliability, creating a motor that started reliably, ran smoothly, survived decades. If you found this valuable, check out my video on worst boat manufacturers that faded into US history. Here's what the marine industry doesn't want you understanding. Those old engines lasted forever because manufacturers built them to survive real-world conditions rather than satisfy emission regulations and quarterly earnings reports. The motors we've discussed shared common characteristics: robust construction, conservative engineering margins, accessible service points, and designs that prioritized function over features. The tragedy isn't that modern motors fail sooner, it's that the knowledge to build truly durable engines still exists, but gets suppressed by priorities having nothing to do with customer satisfaction. Those old 2-strokes and early 4-strokes proved marine engines could provide decades of reliable service.